Hello and welcome to the lecture on 5.2. Today we're going to talk about trigonometric functions of real numbers. Now, what we're going to do first is we're going to start with the unit circle and how we can look at each function and their representations on the unit circle. Suppose that we have our unit circle here. And we have a t value, comes up to this point, call it pxy. Now you need to remember how we graph points. This is the y value, so vertical distance, it would be roughly here. In this case, that's y. And then this is the x value. Also, we draw this. Remember that this length is actually 1 unit because we are on the unit circle, which means the radius is 1. Further recall that t is the radian measure of the central angle. So here, when we write out our t, as we rotate around the unit circle, we get to this point. Remember, there's a t value that's associated with this terminal point, this t. Now, this t is the measure of this angle in radians. So this would be t radians. So what I'm going to do is I'm going to take this triangle, I'm going to redraw it right here. So we have x, y, 1, and t radians. Now, the next thing I'm going to do is just give you the sine, cosine, and tangent of these angles, of this angle t. So sine of t is going to be opposite over hypotenuse, y over 1. Cosine of t is going to be adjacent over hypotenuse, so x over 1. And tangent of t is opposite over adjacent, y over x. Now, having these three functions will allow us to get the other three as well, cosecant, secant, and cotangent. That's what I'm going to give you right here. Let t be any real number, and let p, x, y be the terminal point on the unit circle determined by t. Then, as we already know, sine of t is equal to y, cosine of t is equal to x, and tangent of t is equal to y over x. So in order to find the cosecant, secant, and cotangent, all we do is take the reciprocal of each of these. So cosecant t is 1 over y, secant t is 1 over x, and cotangent t is x over y. This also shows that cosecant is the same thing as 1 over sine. Sine is equal to y. We have 1 over y, so this is the same thing as 1 over sine. Similarly, secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent. Also, tangent is y divided by x, which means it's sine divided by cosine. Cotangent would be cosine divided by sine. Recall? We did this in section 6.2. We had 3 radian measures of angles. We had pi over 6, pi over 4, and pi over 3. And pi over 3 came out to be the point 1/2 root 3 over 2. Pi over 4 is root 2 over 2, root 2 over 2. And pi over 6 is root 3 divided by 2, 1/2. We also went over these in the unit circle video. Should be the last video that we talked about. If we know that these are the terminal points for each of these 3 points, we should be able to find all 6 trig functions of a t value that's associated with these angles. And remember, t is the radian measure. So t at this point would be pi over 6. T here would be pi over 4. T here would be pi over 3. Find all 6 trig functions of t equals pi over 3. Sine of pi over 3. Remember, sine is y, so we look at the y value at pi over 3. T was a real number. In this case, our t is pi over 3. We had a terminal point, pxy. Sine of t is equal to y. So it's the y value in the terminal point. Cosine of t is equal to x. It's the x value in the terminal point. So sine of pi over 3 is the y value in the terminal point associated with t equals pi over 3. So we look at the y value, we get root 3 over 2. Cosine of pi over 3 is the x value in the terminal point associated with t equals pi over 3. We go up to t equals pi over 3, and then we look at the x value, we get 1/2. And tangent of t is y over x. So it's the y value divided by the x value in the terminal point associated with t equals pi over 3. We look at t equals pi over 3, and we do the y value divided by the x value. The root 3 divided by 2 divided by 1 divided by 2. And this will reduce to root 3 when you flip the 1/2 and multiply. In order to find cosecant, secant, and cotangent, you simply take the reciprocal of each respective function. So cosecant of pi over 3 will be 2 divided by square root 3. Also, if you rationalize the denominator, it'll be 2 root 3 divided by 3. Secant of pi over 3 is equal to 2, and cotangent of pi over 3 is equal to 1 divided by root 3, which, again, if you rationalize, you get root 3 over 3. This was the one that you have to rationalize most often, tangent and cotangent. All right, go ahead and try one on the accompanying worksheet. Find all 6 trig functions of t equals 7 pi over 6. Now, you'll probably need to use the unit circle on this one. If you have it memorized already, then great. But if you need to use the unit circle, that's fine as well. We're still learning it, so you do need to understand the unit circle and have it memorized as you move through the class. Otherwise, you will fall behind. Now let's talk about the domains of the trig functions. Later on in the section, we're going to get into graphing these trig functions, but we need to talk about the domain in order to do that. We already know their associations with the unit circle. Sine is y, cosine is x, tangent is y over x. So this is actually going to limit our domains in some cases. For sine and cosine, it doesn't limit at all. The domain for sine and cosine is all real numbers. Tangent and secant, on the other hand, have a limited domain. It's all real numbers other than t equals pi divided by 2 plus n pi for any integer n. And I'm going to get into this in a second and explain it, but for right now, let me finish the cotangent and cosecant. It's all real numbers other than t equals n pi for integer n. Now, tangent, secant, cotangent, and cosecant have restricted domains. And this is actually because of division by 0. If you recall, we can never divide by 0, so any value that makes a denominator 0 means it's not in the domain of the function. So for tangent and secant, remember tangent of t equals y divided by x, and secant of t is equal to 1 over x. Notice that they have the same denominator, namely that it's x. So if we go to the unit circle, so since tangent is y over x and secant is 1 over x, what we need to do is we need to look for where the x value is equal to 0, because those t values, those radian measures, are not going to be in the domain for tangent and secant. We start here, we see that we have an x value of 1. As we rotate around, we have x values that are non-zero, and then we reach pi over 2. At pi over 2, we have an x value of 0. This means that pi over 2 cannot be in the domain of tangent, nor can it be in the domain of secant. Now, if we continue to rotate around, we come across 0, negative 1, where we have an x value of 0 again. Now, since this x value is 0, we know that 3 pi over 2 can also not be in the domain of tangent and secant. Now, if you notice, every integer pi after pi over 2 and every integer pi before pi over 2 will yield another terminal point where the x value is equal to 0. So it can't be pi over 2, 3 pi over 2, and if we continue to rotate around, we would have 5 pi over 2, 7 pi over 2, 9 pi over 2, and so on. We could also go in the negative direction. Negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, negative 7 pi over 2, and so on. Similarly, cotangent is equal to x over y, and cosecant is equal to 1 divided by y. Because cotangent is x divided by y, and cosecant is 1 divided by y, now we're looking for where y is equal to 0, so that we can eliminate those t values from the domain of cotangent and cosecant. So we're going to look on our unit circle at all the terminal points and determine where our y value is equal to 0. And it happens right here, very first point, 1, 0. Our y value is 0. This means that the t value is 0, 0 radians, is not in the domain of cotangent, nor is it in the domain of cosecant, because we have a 0 for our y value, and cotangent is x divided by y, and cosecant is 1 divided by y. If 0 is in the domain of those two values, then we would be dividing by 0, which is not possible. So we look for any other terminal point for which the y value is equal to 0. And we come across one at pi. Now at pi, we have a y value of 0 as well, which means that pi, the t value pi, is not in the domain of cotangent, nor is it in the domain of cosecant. Now we can continue to go around the circle, and we'll see that every integer pi is not going to be in the domain of cotangent nor cosecant. Pi, we have a 0. If we continue to rotate, we have 2 pi, and then 3 pi, and then 4 pi, and so on. We could also go in the negative direction. Negative pi, negative 2 pi, negative 3 pi, negative 4 pi, and so on. So to recap, tangent and secant have a domain of all real numbers except for the angles for which the x value of the terminal point is equal to 0. And cotangent and cosecant have a domain of all real numbers except for the angles for which the y value is equal to 0, because we cannot divide by 0. All right, the next topic I want to talk about is values of trig functions. Let's start by recalling something from a few minutes ago. Sine of t is equal to y, cosine of t is equal to x, tangent of t is equal to y divided by x, cosecant t is 1 over y, secant t is 1 over x, and cotangent t is x over y. I want to remind you that the unit circle is embedded in the xy plane. So every point on the unit circle has an xy coordinate. Those are our terminal points. Many people forget this. If we have a terminal point P, x, y, these are the coordinates of the point. That's all. All right. Now, that being said, when we're in the xy plane, you might remember when x is positive and when y is positive. So in the first quadrant, x is greater than 0, so is y. In the second quadrant, x is less than 0, but y is still positive. In the third quadrant, x is less than 0 and y is less than 0 because they're both negative. And in the fourth quadrant, x is actually greater than 0 because it's to the right of the y-axis, and y is less than 0 because it's below the x-axis. So using these properties in the xy plane, we can figure out what the signs of each of these trig functions will be in each quadrant when t lands in a specific quadrant. Signs of trig functions. In quadrant ever, we have quadrant 1, 2, 3, and 4. Then we'll have our positive functions and negative functions. In quadrant 1, x is positive and y is positive, so all 6 trig functions will be positive. So there are no negative functions in quadrant 1. In quadrant 2, x is negative, y is positive. Y is positive, y is positive. So sine and cosecant are both positive, but all the other ones are negative because we have a negative x. Our x is a negative value, so x will be negative, which means cosine is negative. X is negative, which means secant is negative. X is negative and y is positive, so tangent is negative. X is negative and y is positive, so cotangent is also negative. We have cosine, secant, tangent, and cotangent. In quadrant 3, we have that y and x are both negative. You have to be careful with this one. Tangent and cotangent will both be positive because y is negative and x is negative. So we have a negative divided by a negative, and that negative cancels. So we would have tangent and cotangent as positive trig functions in the third quadrant. All the other ones are negative. So cosine, secant, sine, and cosecant. And in quadrant 4, x is positive but y is negative. So cosine and secant are positive. And all the other ones are negative, much like quadrant 2. So we get this. And another graphic in order to show you how to remember this. Many people use the anagram. All students take calculus. In quadrant 1, all are positive. In quadrant 2, sine is positive. In quadrant 3, tangent is positive. And in quadrant 4, cosine is positive. All students take calculus. So all are positive, sine is positive, tangent's positive, cosine is positive. And their reciprocals are obviously the same sign as them. Next, I'm going to go over a guideline on how to find the trig function of t-values. Quick way to find the value of a trig function of any real number t. 1. Find the reference number associated with t. 2. Note the quadrant where the terminal point determined by t is, and find the sign. And 3. Evaluate the trig function using the reference number and add the sign. So this is actually how we generally find trig functions of t-values on the unit circle. We do it this way, but it's sort of inherent. We don't actually think about each step. We just kind of do them very quickly. I'll show you exactly what I mean with this example here. If we're trying to find sine of 37 pi over 4, there's 3 things that we do. We find the reference number, which will be t bar. Now remember, t bar is the shortest distance from the terminal point determined by t to the x-axis. So if we have our unit circle, suppose that our point is here, we're looking for the shortest distance along the unit circle to get to the x-axis. That would be this point, if you've forgotten what the reference number is. Now in this case, t actually lands in quadrant 3. Goes around a few times, but it lands in quadrant 3. The reference number is going to be pi over 4. And since it's in quadrant 3, and we know that sine is negative in quadrant 3, we know that our final answer is going to have a negative. So this will equal negative sine pi over 4, where pi over 4 is t bar, that's our reference number, and this sign is because we're in quadrant 3. So normally sine of pi over 4 will be positive because pi over 4 is in quadrant 1. Because 37 pi over 4 gives us a terminal point in quadrant 3, we need to add this negative. Now previously I noted this, but I didn't actually write it out. So now I'm going to write it out. Recall? sine of t is equal to y, cosine of t is equal to x, tangent of t is equal to y divided by x. Similarly, cosecant of t is 1 over y, secant t is equal to 1 over x, and cotangent t is equal to x divided by y. Now, I noted previously that sine is equal to y, and cosecant is 1 over y, which means cosecant is 1 over sine. I'm going to note this right now in writing. So cosecant of t is equal to 1 divided by sine of t. If we replace y with sine here, then we would have 1 divided by sine. And we can do that because the y values are the same for a terminal point. Secant of t is 1 over cosine, and cotangent of t is 1 over tangent t. For example, let's find secant of pi over 3. We're looking for the value of secant, cosecant, or cotangent of an angle. All we need to do is figure out their respective reciprocal, and then we can just write out our answer. So here, I know that this is the same thing as 1 over cosine pi over 3. So really, when I'm looking for secant, I don't really care what secant is specifically. I care what cosine is, because I know secant will just be 1 divided by whatever cosine is. So we find cosine pi over 3. Cosine of pi over 3 is 1/2, which means secant of pi over 3 is 1 divided by 1/2. So secant pi over 3 is equal to 2. The next thing we're going to talk about is even and odd properties, but I need a graphic in order to show you why these are the way they are. Start here. So suppose that we have our unit circle. We have a t value that comes up to this point. And we go in the opposite direction, the same t value. So at this point, this would be negative t. So remember that we have p, x, y here. And this point would be p, x, negative y. Because they have the same x value. Well, they should have the same x value. I just drew it wrong. But they have the same x value. So this x matches this x. The only difference is that the y is negated. This distance, this vertical distance, is the exact same thing as this vertical distance, except we're going down here and we're going up here. So we have a negative y value, a positive y value. So that being said, if we were looking for sine of negative t, we would end up with the y value of this terminal point, which is negative y. We get negative y. But notice also that y is the same as the sine value of positive t. So we would have negative y, and this y becomes sine of positive t. So we get negative sine t, which means that sine of negative t is equal to negative sine of t. We can do a similar thing with cosine. Cosine of negative t is equal to x. It's the x coordinate of this terminal point. So we just get x. That x is the same as this x. So it's actually equal to cosine of positive t. Now we have cosine of negative t is equal to cosine of positive t. And then lastly, tangent of negative t is equal to negative y divided by x. The y value of this terminal point divided by the x value of this terminal point. Now if we move this negative off, we get a negative y divided by x. And then y over x would be the y value here divided by the x value here, which means it's the tangent of this positive t value. So we'd end up with negative tangent of positive t. Now, Let's actually get into the even and odd functions and define each of them. Now let's define, sign, formalize. Now let's formalize which functions are even and odd. First, we need to recall what even and odd functions are. So recall that a function f is even if f of negative x is equal to f of x, and is odd if f of negative x is equal to negative f of x. So, which trig functions fit these properties? So if I plug in a value with a negative, that negative just gets absorbed in the function, meaning it just drops, it just goes away completely. This is an even function. We have a cosine of negative t, so we're inputting a negative value, and we get the same thing as cosine of positive t. So that negative is just getting absorbed into the function. So we can say that cosine is even. A function is odd if f of negative x is equal to negative f of x, meaning that we can sort of pull this function out of the input value and put it on the output value. And we can see that with sine and tangent. Sine of negative t is equal to negative sine of t. So we have a negative input, but over here we have a negative on the output. Negative input, a negative on the output. So we can say that sine t and tangent t are odd. I'll make a quick note before we move on to the next topic. These properties, the even and odd properties of sine, cosine, and tangent, are generally more useful in the theory of problems. So we'll use them mostly when deriving stuff or using these when discussing the theory behind the trigonometry instead of actually in practice. It can be helpful in practice, but usually you won't see that until about calculus. All right, the next topic I want to talk about is fundamental identities. First, let's define what an identity is. Now, you all should know what an equation is already, so we're going to skip that definition. An identity is an equation that is true for any input. So, for instance, in this case, think about the identity square root of x squared is equal to the opposite value of x. No matter what x value I plug in, this equation will hold true, always. This is an identity. A trig identity is an identity involving trig functions. So for example, we just gave one. Sine of negative t is equal to negative sine of t. This is a trig identity. No matter what t is, this equation will always be true. So it's an identity, and it's involving trig functions. And we're going to give a few fundamental identities. Reciprocal identities. Now you should star these in your notes if you're taking notes, because they come back in chapter 7, where we deal almost entirely in identities. So cosecant t equals 1 over sine. Secant of t is equal to 1 over cosine t. Cotangent t is equal to 1 over tangent t. Now, of course, we also have that tangent t is equal to sine over cosine, so sine of t divided by cosine of t. And cotangent t is equal to cosine of t divided by sine of t. I don't know why books do this. They put these two identities in with the reciprocal identities. I don't know why they do it, but most books do this. So we can just give them here. It doesn't really matter as long as you know the identity. Tangent is sine over cosine, cotangent is cosine over sine. Now here's another really big one, the Pythagorean identities. Now I'll prove the Pythagorean identities for you, but they are sine squared t plus cosine squared t is equal to 1. Tangent squared t plus 1 is equal to secant squared t. And 1 plus cotangent squared t is equal to cosecant squared t. We're going to prove these on the next slide. I want to go back for a second. These are very, very important identities. All three of them. Mostly this one and this one, but all three of them are very important. If you know this one, you should be able to prove these two pretty easily, and I'll show you on the proof. But I cannot stress enough how important both of these categories of identities are. Again, in Chapter 7, it'll come up, and we'll deal almost exclusively with identities. So first, recall, sine of t is equal to y, and cosine t is equal to x. Also recall, the unit circle is x squared plus y squared is equal to 1. This is the equation of the unit circle. Now we can prove this another way using triangles, but it doesn't actually matter. Because triangles can be any size, so when we use triangles in the unit circle, we're going to get the unit circle equation anyway. So if we plug in y for y, we have y is equal to sine, so we plug in sine for y. X is equal to cosine, so we plug in cosine for x. We get cosine squared t plus sine squared t is equal to 1. One Pythagorean identity down. Now we use this one to prove the other two. So suppose I want to prove the next identity. What I'm going to do is I'm going to take this identity that I have, and I'm going to divide both sides by cosine squared. We have 1 over cosine squared times cosine squared plus sine squared equal to, and 1 times 1 over cosine squared t. So remember, 1 over cosine squared is the same thing as secant, but when I multiply this in, I'll get cancellation here, and I'll just have a 1. And when I multiply this in here, I get sine squared t over cosine squared t. And then on the right, we just have 1 over cosine squared t. Now you can pull this square out, so you would have sine over cosine quantity squared, which will give you tangent. So this is 1. So this becomes 1 plus tangent squared t is equal to secant squared t. Because on the right, 1 over cosine squared is the same thing as secant squared. Similarly, if we multiply both sides by 1 over sine squared, we'll get the opposite Pythagorean identity. So when we distribute this in, we'll see in a second. Over sine squared here. And when we distribute this into both of these, we'll have cosine squared over sine squared. Sine squared divided by sine squared is just 1. And then on the right, we have 1 over sine squared. So we get cosine squared over sine squared is cotangent squared t plus 1 is equal to cosecant squared t, which is this guy. And that's it for those 3 identities. We'll need to use them for this particular problem, but a lot of problems that you will deal with in this class, you won't need to use these for in order to solve for all 6 trig functions. Suppose sine of t is equal to 2/3, where the terminal point is in quadrant 2. Find all 6 trig functions of t. We already know that sine of t is equal to 2/3. We can start there. Right? This also implies then that cosecant t, which is 1 over sine, is going to be 3/2. Remembering that cosecant t is equal to 1 over sine t. So I have sine, I just take the reciprocal, and I get cosecant. Now this is where a lot of students stop because they don't know what to do next. Just think about it for a second. We have relationships with sine and cosine. Specifically, sine squared t plus cosine squared t is equal to 1. So if I know what sine is, I can solve for cosine. So if we plug in sine, we get 2/3 squared plus cosine squared t is equal to 1. 2/3 squared is 4/9. So if I subtract that over, I get cosine squared t is equal to 1 minus 4/9, which is 5/9. We take the square root of cosine of t, and we're going to get two answers, plus or minus square root 5 divided by 3. Now there's a reason we have two different answers. These are the two solutions to this equation. Now they're not both solutions to this problem, they're both solutions to this equation. Remember, this equation is the equation of a circle, so if we're given a y value, there are two possible x values, a positive x value and a negative x value. What we need to do is determine whether cosine is positive or negative by looking at the terminal point. The terminal point is in quadrant 2, which means that the x value, which is what cosine is negative, because x is negative in quadrant 2, so we use the negative cosine value as our solution. So now we have cosine of t is equal to negative square root 5 divided by 3. This also gives us secant of t, because secant is the reciprocal of cosine, so you simply flip the fraction, negative 3 divided by square root 5. Now all we need to do is find tangent of t and cotangent of t. Now there's two ways to do this. We know that tangent has a relationship with secant through the Pythagorean identity, but that is the harder way to do it. You don't need to use the Pythagorean identity in order to do this. Let's work a little bit smarter. Remember also that tangent is sine divided by cosine. So all I need to do is take 2/3 and divide by negative square root 5 over 3. So when we flip and multiply, we end up with negative 2 divided by square root 5. Cotangent is cosine over sine. So we would do negative square root 5 over 3 divided by 2/3, flip and multiply, and we get negative root 5 over 2. Like that. Now we've solved for all 6 trig functions. So we are done. All right, I want you to go ahead and try one on the accompanying worksheet. Cotangent of t is equal to 2, where the terminal point determined by t is in quadrant 3. Find all trig functions of t. You just need to find all 6 of these in almost the exact same way. You'll know what cotangent is because it's the reciprocal, and then you use a Pythagorean identity that involves tangent in order to find another one, and then you can continue from there. Another type of problem using the Pythagorean identities is this. If the terminal point determined by t is in quadrant 3, write tangent t in terms of sine of t. All right. Now this is a little bit tricky. You have to understand what we're trying to do here. So let me give you a little bit of a note. When we have a function in terms of x, on one side you're going to have x's most of the time, but this is a function that's in terms of x. If I had a y here, now it would be a function in terms of x and y. You could just have constants, or constant times x. This is a function in terms of x. What it means is that we have x terms over here, terms being groups of variables and constants. This. This would be in terms of x. Right. So when we ask for a function in terms of sine, our answer needs to involve sines and only sines. No other trig function. So what we're going to end up with is tangent of t is equal to something over here that involves sine functions. Let's start with the very basic one. Tangent of t, we already have a small relationship with sine. Sine of t divided by cosine of t. Now this isn't in terms of only sine. This is in terms of sine and cosine. I want it to be in terms of only sine. So what I need to do is I need to write cosine in terms of sine. If we can do this, we'll substitute the corresponding terms of sine in place of cosine, and then we'll have our function done. Tangent will be in terms of only sine. So our relationship between sine and cosine is sine squared t plus cosine squared t is equal to 1. Now when we're trying to solve cosine in terms of sine, we're trying to get cosine alone on one side to be equal to something with sines in it. So we'll have cosine squared t is equal to 1 minus sine squared. Take the square root and we get cosine t is equal to plus or minus the square root 1 minus sine squared t. This fraction, or this radical does not reduce, so don't reduce it. This is a common mistake amongst students in algebra, trig, and even up into calculus. Now the problem here right now is that I have cosine is either positive square root 1 minus sine squared or negative square root 1 minus sine squared. But it can't be both. It's one or the other. So we have to use the last piece of information here. Our terminal point determined by t is in quadrant 3. So we look at cosine and we say in quadrant 3, is cosine going to be positive or is it going to be negative? Cosine's negative in quadrant 3, which means we use this negative sign here. And we ignore the positive. So now, because I know cosine in terms of sine, I can replace this cosine with this expression here. So we then have tangent of t is equal to sine of t divided by negative square root 1 minus sine squared t. Now we have tangent in terms of only sine. There are no cosines, there are no other trig functions, it's just sine. Try one on the accompanying worksheet. If the terminal point determined by t is in quadrant 4, write cotangent of t in terms of only cosine t. You're going to basically follow exactly what I did in the previous example. All right, that's going to be it. I will see you all in the next lecture.